Welcome. This presentation will cover Internet of Things networking, focusing on the protocols and network architectures that make it all possible. We'll explore key protocols, different connectivity options, various architectural patterns, and crucial security considerations within the Internet of Things landscape. So, what exactly is the Internet of Things? The Internet of Things refers to the network of physical objects. These objects are embedded with sensors, software, and other technologies. This enables them to connect and exchange data with other devices and systems over the Internet. Think of it as a vast web of interconnected devices, all communicating and sharing information. This slide shows some of the devices like smart home, car, watch, industry equipment, thermometer, and smart light. Now, let's dive into some of the key communication protocols that enable Internet of Things devices to talk to each other. First, we have MQTT, which stands for Message Queuing Telemetry Transport. It's a lightweight publish or subscribe messaging protocol specifically designed for devices with limited resources. Key features include low bandwidth usage, a publish or subscribe architecture, and different quality of service levels to ensure reliable message delivery. Next up is CoAP, that is Constrained Application Protocol. It is a specialized web transfer protocol tailored for constrained nodes and networks within the Internet of Things. It follows a representational state transfer, that is RESTful architecture, operates over User Datagram Protocol, that is UDP, and includes built-in discovery features. Finally, we have Hypertext Transfer Protocol, that is HTTP, and Hypertext Transfer Protocol Secure, that is HTTPS. These are the foundation of data communication for the World Wide Web, and they've been adapted for Internet of Things as well. They offer representational state transfer, that is RESTful Application Programming Interface, that is APIs are widely supported, and provide security through Transport Layer Security, that is TLS, or Secure Sockets Layer, that is SSL. Let's explore some additional protocols commonly used in Internet of Things networking. First, there's Zigbee. It is a low-power, low data rate wireless communication protocol. It is designed for personal area networks. Its key features include mesh networking capabilities and very low power consumption. Then we have Bluetooth Low Energy, or BLE. It is a wireless personal area network technology. It is designed for short-range communication. It's known for its ultra-low power usage and its ability to provide short-range connectivity. Finally, we have Long-Range Wide Area Network, that is LoRaWAN. It is a protocol specifically designed for low-power, wide area networks with long-range capabilities. It offers long-range transmission and excellent battery efficiency. Now, let's discuss some common network architectures used in Internet of Things deployments. The first one is centralized architecture. In this setup, all devices connect to a central server or cloud platform. Data processing and decision-making primarily occur at this central point. On the other hand, we have distributed architecture. Here, devices communicate directly with each other in a peer-to-peer network. Processing is distributed across multiple nodes, allowing for more localized decision-making. Let's explore edge computing in the context of Internet of Things. Edge computing involves processing data closer to the source of data generation. Instead of relying solely on the cloud, this architecture brings computation and data storage closer to the devices themselves. There are several benefits to this approach. First, reduced latency, since data doesn't have to travel as far for processing. Second, enhanced privacy and security, as sensitive data can be processed locally. Third, bandwidth optimization, reducing the amount of data transmitted to the cloud. Now, let's talk about fog computing in Internet of Things. Fog computing extends cloud computing to the edge of the network. It creates a distributed computing infrastructure. It strategically places data, compute, storage, and applications in the most logical and efficient location. It resides between the cloud and the data source. How does this compare to edge computing? Well, edge computing typically happens directly on devices. It is for local processing, resulting in the lowest latency. Fog computing, on the other hand, occurs between the edge and the cloud, enabling more distributed processing with low to medium latency. Now, let's address some of the key security challenges in Internet of Things networking. First, we have device security. Internet of Things devices often have limited computational resources. This makes it challenging to implement traditional security measures. Also, many devices ship with default credentials and lack regular security updates, making them vulnerable. Some solutions include secure boot mechanisms and hardware security modules. Next, we have network security. Internet of Things networks often connect previously isolated systems to the Internet. This creates new attack vectors. Insecure communication protocols can expose sensitive data during transmission. Solutions include network segmentation and encrypted communication protocols. Then comes data privacy. Internet of Things devices collect vast amounts of potentially sensitive data. Ensuring proper data handling, storage, and compliance with privacy regulations is critical. Solutions include data minimization principles and end-to-end encryption. Finally, authentication is important. Ensuring that only authorized devices and users can access the Internet of Things network can be challenging. This is especially the case in large-scale deployments with diverse device types. Solutions include mutual authentication and certificate-based identity. Let's take a look at some future trends shaping Internet of Things networking. First, fifth generation, that is 5G integration. Fifth-generation networks will provide the high bandwidth, low latency connectivity. This is needed for advanced Internet of Things applications. It will enable massive Internet of Things deployments with up to 1 million devices per square kilometer. This enables real-time applications like autonomous vehicles and remote surgery. Next, artificial intelligence at the edge. Artificial intelligence and machine learning capabilities will increasingly move to edge devices. This enables smarter local decision-making without constant cloud connectivity. This ensures that devices will become more autonomous, with improved privacy and reduced bandwidth requirements for data processing. Finally, self-healing networks will evolve. Internet of Things networks will automatically detect and recover from failures. They will reroute traffic and optimize performance without human intervention. This increases reliability and resilience for critical Internet of Things applications. Also, it reduces maintenance costs and downtime. The future of Internet of Things networking will be characterized by greater intelligence, autonomy, and seamless integration across diverse technologies and domains. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.